We're going to hope this doesn't crash for the fourth time today, and here we are. All right, just a couple of things. First thing is on, I think it was 132. It was one of these things. I think it was this one. I asked you to show the direction on the angle, and some of you just threw down an angle. And just, just be sure if I'm asking you to show a direction, to clearly show it, to just be sure you're indicating that. Now, I might have had a typo on this in the answers. I can't remember. But anyway, I didn't take any points off on this. But on that one, the angle came up to be 74.4, but it's down and to the right. So you want to indicate that in some fashion. Okay, so trying to remember which one this was. It was 122. And I might have a typo in that answer key. I'm not sure, so I didn't take anything off. But yeah, 132. Thank you. Yeah, 132. And so what I was looking for was something like that, 74 degrees. You could have also called it minus 74 degrees. But just be watching for things like that, okay? Because I did on that one ask specifically for the direction, okay? So that was that one. So for those of you online, I've graded that second homework, and so we're just going over that, okay, a bit. Just not a huge amount, but a little bit. All right, so that's that one. And then the other one I'd mention is that double projection. Some of you are kind of, I think, maybe working out that angle by kind of reverse engineering it from the answer, perhaps. I'm not quite sure what was going on with that. But anyway, the way to set up this F1 vector on 143 is you've got a double projection there. So you want to take the magnitude of the force, which is 2,000, and then multiply that through the projection. Now what you're going to do to get onto the x-axis is you're going to go cosine 72. That'll get you down here into the xy plane. And then an additional cosine 41 then would get you over to the x-axis. So that would be the I component, and there's the 41-degree angle. So that's a two-step process there. Now we also have a J component. And so what that one's going to be is you're going to have cosine 72. And then what you're going to want to do is get over to the y-axis. So cosine 72 gets you down into the plane. And then what you're going to do this time is cosine of the angle from that projection to the xy plane, which is 41 plus 90 more, and that'll get you the J. All right. And then the last one would be the K. Now that's this angle right there, and that's 18, which is 90 minus 72. So that last one there will be cosine 18. Okay. All right. So that's how you'd work that vector out. So you just kind of, to get two of the angles, or two of the unit vector components, maybe I should say, that'd be a better way to word it. You've got to project it down into the xy plane, and from there project it over to the x and y axes. So the cosine 72 gets you down into the xy plane, and then the cosine either 41 or 131 gets you over to the x and y axes. And then the last one, you've got 72 up from the xy plane. You got to go 18 more to get up to the z-axis. Okay. So we got a test coming up a week from today, right? I'll get you a review for that hopefully tomorrow, okay? We'll just go over that a bit. We're getting into new material now that isn't on the test, but we always got to kind of keep on going. So we're off to the next one here. Any other questions on that homework that I just handed back?
Is there anything you wanted us to know for 140?
Yeah. Okay. Right.
Is torque going to be on this test?
Yeah. Yeah, because it'll be up through moment, torque, whatever you want to call it. Yeah. So they'll be through that. All right, now let's have a look, if we're good at this, good on this, I should say, at the next little step down the line. Now this particular part of torque or moment won't be on the test, but up through the 3D, the 2D and the 3D moments that we did that you turned in for your, or you will turn in, right? Yeah, on Wednesday for your last homework. That's what the homework will be through, okay? Okay. So that's, I don't know what problem number that is, but maybe if I started talking about it, I should figure it out. So
201, 211, 212.
yeah, that sounds good. Yeah, 201, 211, 212. That's where that's as far as the test will go. All right.
Is just out of curiosity, the last homework for the week, and then we had the review for the next test?
I'll probably get you maybe one or two little things for Wednesday. Yeah. Yeah, 201, 202, 211. Yeah. Okay, we're good? Okay. All right, now we've talked about moment, and the way we introduced moment was if you just have probably the best analogy is a wrench. If you've got a wrench and it extends out, and then you've got a bolt in here, and you apply a force, you take the force times the distance, and you get a moment, right? I mean, that's basically it, if the force is perpendicular to the distance, okay? And that's how you come up with a moment. But there's another type of moment that you can generate as well. It's what's called pure moment, or sometimes called a couple. All right, now a couple doesn't have any associated force. There's no net force on a couple. So if you want to open this valve, what you're going to do is grab the whole valve and turn it. So you're not pushing the valve handle, you're not pushing it left, right, or up or down or anything. You're just twisting it. So a couple or a pure moment is just a twist. Okay. Now here's a couple doorknobs, and if you want to open the doorknob, I think we know how to open doorknobs. We push down on the handle there, don't we? And that will open the doorknob. But what you can also do on this doorknob is just twist it. Okay. And hopefully you're not pushing or pulling on the knob on the one on the left. You're just twisting it. So that's what's called a couple or a pure moment. There's no associated force with it. Okay. You okay with that? They're different. They both result in a twisting action, but they're generated just a little differently. All right, now let's have a look then at some of this stuff here in the book, all right, or the packet, I should say. We're on page 330, I think. Now, really, there are forces when you do this, all right? But the thing is that they all create the same sort of twist. So if you were to take down what's happening in the shaft of that valve, what you have are a bunch of little forces all going, let's say, counterclockwise. All right, and the assumption here is that they're all equal to one another. So, I just show 8 here, so I got F1 going that way, and then I got F5 going the other way. See, they make up a pair that is twisting counterclockwise, So there is a moment associated with those, but the force cancels out. And for every one I've got here on one side, I've got a force going the other direction on the other of equal magnitude. So everything cancels out as far as the forces. That's the idea behind these couples or pure moments, is for every force you got on one side pushing one way, you've got a force on the other pushing the other way. They create a moment, but they have no net force. So that's the idea. Okay, and if you take this and boil it down to its simplest expression, oh, come on now, you can't do that. I'm just trying to pick a color. I mean, it just isn't right. Okay. This thing's been locking up on me all day. I'm unhappy. End task. Set control panel. Start up software. Open file. Can't find file. Pure moment. There we go. Oh, that's interesting. Okay. All right, so I don't know if I'll recreate my beautiful color drawing there again, but you get the idea. So for every force we've got on one side, we've got another pushing the other direction. But being as they're on opposite sides of the center point, the net force is zero. You still get a twisting action, but the net force comes out to be zero. That's the idea, okay? All right, now the simplest expression of this that you can get down to is a couple, and that's where this term comes from. I always found it to be kind of an odd word for this. I kind of prefer pure moment or just a twist or something like that, but in the textbooks they'll call this a couple because the simplest model you can use to demonstrate this effect is just two forces on either side of a point going opposite directions. And that'll get you a net force of zero and a twisting action is what it'll get you. So they refer to that as a couple. Now, if you want to find the moment of that particular couple down here with the forces equaling each other, going opposite directions on either side of point O, if we want to find the moment about O, and we have the perpendicular distance between the forces, which is D, okay, what we can do there is, I don't have that either, okay, is calculate that out. So what I'm going to have there for the top is I'm going to have F times D over 2, because D actually extends from one force to the other. And then for the one on the bottom, I'll have another positive counterclockwise moment, which will be F times D over 2. So I'll get 2 FD over 2, otherwise known as the force times the offset distance. Okay, so the general formula for a couple is F times the distance between the two forces, the distance being perpendicular. Now you could also do it with a cross product if you wished, okay, where R does not have to be perpendicular. Okay, so that's the simplest way to express this idea of a couple. Two forces oppositely directed on either side of a point. Yeah, question there?
If we multiply the distance by the force, if the force doesn't exist.
The forces, in the way I'm drawing it up, they do exist because there's one on either side. The net force is zero. So I guess you could say the net force doesn't exist, the sum of forces, because it's zero. But there are individual forces that generate it. For every one on one side, it's balanced by another on the other side that goes the opposite direction. So it's kind of like components versus the total, I guess you could say. Okay. All right. Other questions? All right, so an example is just twisting that valve to open it. You know, if you look at the shaft between the handle and the oh, the gate on that valve, you might call it. So we're looking at the valve stem there. As you twist it, you'll have a force here and a force there, and a force here and a force there, you know, et cetera, et cetera. I used 8 on the previous sketch. Now I'm using 4, however many you use, they cancel out. And if you wanted to, you know, you could go all calculus on this and get an infinite number of forces, and, you know, it'll still zero out, right? Okay, so, yeah. All right, thanks. All right. All right, so, you know, there's lots of examples of this. Again, I can open that door by pushing on the handle. Or I could turn the handle. Either way, and in both cases, I'm getting a twist. One on the left has no net force, one on the right does. Okay, I can apply a force at an offset to my jar here, or I can just use my hand and twist it. Same thing. Okay. Now here's a couple right here if I'm trying to break that lug nut loose. I could go like that, right? Or I can go like that. Okay. Now, see how that upper left one is a couple? There's a very good example of a couple. And there actually are 2 forces on that should balance out. Whereas the one on the lower right is a force times the distance. Okay. All right, let's have a look here at this next little funny looking free body diagram we've got here about halfway down the page. Let's look at the effects of this couple on point A. Let's start with that, okay? Let me do this. All right, let's start with the moment about A. And what we've got here is 300 newtons. And we're going to call that 3 centimeters. So that'll be times 3 centimeters, times 0.03 meters. And that would be positive for the top one. And then the one below is 300 newtons. Times 0.03 meters also positive by the moment convention. And there's a good example of signs on 2D moments. See, the force left and the force right both cause a positive moment, don't they? So there's no direct connection between the force sign and the moment sign. It's never quite that simple. But for the moment there, we'll take 9 Newton meters plus 9 Newton meters. And what we'll get out of that is we'll get 18 Newton meters, right? So why don't you find the moment about B? So let's look. We found the effect at A. It's an 18 Newton meter positive moment. What's the effect at B of those 2 forces? So if we focus on that and look at the effects at B, what would they add up to equal? So if we take moments about point B, what are we going to get? Oh, this isn't looking good. doing all right on that? What are we getting?
24?
24? 24? Anyone get something different? Maybe not. Just don't care to comment on this. What's up? Anybody got something different in 24? I did. What's that?
Pretty sure it should be 18.
18?
Go.
Yeah.
Wherever you go, it's
Okay.
you
Yeah.
got a you
Yeah.
got a length and then length and then you're subtracting that for the same thing. the same
Okay.
force
Yeah, they're gonna
multiplier.
kind of cancel out, right?
Yeah.
Yeah. So I got 18. Yeah. Anyone else getting 18 on that? Okay. How about the one after, about C?
Why does it have NP?
Well, it wants to do the arithmetic and a second time to add it up. Okay. All right, so if we do MC, we get something a lot like 18, do we? Maybe? So it doesn't matter where we go, huh? We get these canceling effects of the lengths and we get to 18. Okay, we're good? Okay. Now, this is a nice thing about being in engineering, right? So we kind of prove that wherever it is, it's going to be 18. Now, if this were a math class, I'd be taking limits going down to 0 and pulling in the mean value theorem in there some way, and we'd be really working at this. Yeah.
These are pretty easy for this because you do have the same forces.
Yeah, as long as the forces have the same offset, they're going to affect every point on that object the same with 18 Newton meters, right? So it doesn't really matter where you are on the object. Every point is being twisted by 18 Newton meters. We okay with that? Okay. Can we illustrate that? You ever start to change a tire and not have the parking brakes set? If you've got a tire that's free to rotate like you would on a front tires on a car with a clutch. Clutch is this thing, it's a third pedal. Used to have these back in the Stone Age. They were like got two plates that spin, got a pedal on the floor. If they're broken, you probably want to take them to someone who knows what they're doing, but I've never fixed a clutch myself. But anyway, okay, so if that wheel's free to spin, what happens if we start turning the lug nut there and it's still kind of locked? The whole wheel's going to spin, isn't it? Now notice the moment is being applied about the nut, right? So when you got your lug nut, your lug wrench, you're turning the moment about that point, yet you make the wheel spin about the center, about the axle, okay? So what you're doing is you're taking the moment that you're applying to that lug nut, and it basically is being transferred over to the axle, to that center bolt there, okay? You all good there? All right. Another one of my finely crafted models here for in-class use. Okay, so here we go. So that's the front of this little board I've got, which is actually a chunk of my siding. Got in a bunch of dry rot on my chimney framing. Spent a couple summers hacking away at that. It's one of those little weekend projects that turned into a month project. Lots of fun there, but there we go. So here's the back of the board. So these are the little axles here, and then I've got those two bolts attached. So let's say I hold the board on the back by this axle right here. So that nut isn't really tight. I'm free to spin about that. And let's say I apply a force or a couple to this handle right here like that. What's going to happen about that axle when I do that? See, I'm not doing anything tricky. I'm just turning about the knob. But where does it spin about? See, that's what's going on there, okay? I can make this object spin about the bolt, about this axle right here, even though I'm applying the moment at the knob, okay? I can do the same thing, about here too if I want. Now, how about this wing nut here? That's really kind of a couple, isn't it? Because if I spin on that, I'm going to push on this side and push on that side. Nice couple there, and I can make it spin about that other one, can't I? Okay. So that's the idea. You can take that couple about any point on the object, and it's also applied to any other point on the object. Okay? Y'all good with that? A little odd perhaps, but that's how these work. And yeah, the idea there is kind of like, Steve was saying there, it's you get cancellation. Yeah, sure, this went from 0.03 to 0.10, but this one went from 0.03, actually it's a positive 0.03 to let's see, I've kind of got myself tied up here a little bit, but I'm moving by 0.07 here, aren't I? And here I'm moving by negative 0.07 is essentially what I'm doing. The two effects cancel each other when it comes to the moment. Here I'm going from 0.03 to 0.15, so I'm going 0.12. Here I'm going from 0.03 to a negative 0.09, so I'm going down by 0.12. As long as I just move to some other point on the object, I'm changing both moment arms by the same amount, essentially. I'm getting some interaction of the signs depending on where the point is in relation to the original point, but the effects on the moment arms compensate for each other is what happens. So I get the same net moment about any point on that object. Okay. So keep that one in mind, okay? That idea of moments being transferable when they're pure moments. Okay. Not only are they transferable, but they're additive. So that example there, I got 30 Newton meters, 40 and 50. They've got different signs on them. Got three couples there. I can just add them up and get the net moment on that object. Okay. So that's got 60 Newton meters. You could call it negative 60 or 60 clockwise. Same thing regardless. Okay. So the couple affects every point on the object in the same way. What do you suppose the most common couple you'd find in industry would be?
First of all, it's a screwdriver. As I think an electric screwdriver.
Okay, yeah, screwdriver would work. Dial. I got a lot of these pictures. There we go. I'd say a motor would be my choice, okay? Motor just puts a torque out on that central shaft. It's not pushing left or right or up or down. It's just spinning is all it does. Okay. So yeah, there's other examples. Yeah, a screwdriver is a nice couple. There's other devices you could run into. Okay. So you'd model that as a couple. Okay. Okay, let's say this motor outputs, and I don't have this copied down, you have to draw this one up. Let's say we've got 40 foot-pounds of torque. What weight can it lift at constant velocity? And think about what we just went over and apply it to this little problem here. What I'm doing here is kind of a transference from a couple to a force times distance moment. So if that thing puts out 40 foot-pounds, and I've got that pulley on there, what weight could I lift at a constant velocity? Meaning, what I mean by that is no acceleration. You can deal with it by using statics, is what I mean by that. Watch your units, okay? if you look at trucks, they talk about the torque they generate. Same sort of idea. The moment coming out of the engine on the drive shaft. But they talk about torque and power, right? Torque is just the moment coming out of the drive shaft. Power is the moment times the angular speed. Converted from RPM into radians per second. Yeah. The angular speed that you use multiplied by the torque.
Double tick mark means inch, right?
So that's 6 inches there for that radius of that pulling. And this is a good example of how to use dimensional analysis too, if you're not quite sure how to proceed. If you just do some simple dimensional analysis on this one, you can figure it out. I used to tutor math and science and stuff at a community college, and I didn't remember much physics, but I remember dimensional analysis, and I could solve an awful lot of physics. Dimensional analysis, you guys have to work out some fashion. This isn't a couple here, he just got one force. Back into what the force is based on that offset distance. Something like that. You know, the voltage is, but the voltage. So 80 pounds. Just follow the units through if nothing else, okay? So what you got coming out of that motor is 40 foot-pounds, which is a couple, just a twist. And then if you could look at this, you know, you're turning the motor there clockwise, aren't you? So if you kind of cut your free body diagram like that, you know that you get like a tension pulling down. If it's lifting at a constant velocity, it's in equilibrium. So the moment generated by this tension here, force times 6 inches. Notice that's not a couple there, it's just a force and an offset. So F times 0.5 feet should equal the torque or the torsion or the moment or whatever it is you want to call it there coming out of that motor. So you get 40 foot-pounds is F times 0.5 feet. You can back into F, it's 80 pounds.
Can you refer to torque on a truck? What is that?
It's the motor, it's what's coming out of the drive shaft, basically, out of the motor. It's the torque. You could work that to the wheels and kind of find the force applied to the ground, which pushes the truck. That's basically how that would go. I'll give you one more for Wednesday. Why don't we look at a quick picture of that? We got a couple minutes, so why don't we do that? That'd be the 18th, wouldn't it? So are there just 3 due on the 18th, or have I lost count? There's 4. This will be 4. Okay, that's good. So that's 221. We also have, what is it, 201, 202, and 211? Is that right? Okay. Now let's have a quick look at 221. See what we got. Oh, come on, open up. All right, go ahead and do that and see if I care. Okay, here we go. Open. For a moment, equilibrium. Today, I guess. Browse. There. Oh, we're to the homework too, aren't we? So this problem here, I think it's 221, we've got 2 hole saws. Now hole saws are just saws that attach to drills. They just spin in a circular motion and cut a hole out of whatever material it is you're working through. Commonly used when you're working on a door. So there's some hole saws. You see how they attach to a drill and they're spun and they just have teeth on them and they just cut a hole through a door or whatever you're looking at cutting a hole through. So they'll generate a moment there, a couple. So I've got the couples there shown for the 2 hole saws A and B. And what I'd like to know is if those couples are applied, what will these forces be at C and D? So that's what I'm looking for on that.